DevOps is a modern software engineering approach that unifies development and operations into a single collaborative practice. Its purpose is to accelerate software delivery, improve quality, and ensure system reliability. In traditional models, development teams focused on building features, while operations teams were responsible for deploying and maintaining them. This separation often created delays, handoff challenges, and limited accountability. DevOps addresses these issues by promoting shared ownership of the entire lifecycle, from code creation to deployment and monitoring. At its core, DevOps is not just about technology. It is a cultural and organizational shift. Teams adopt practices that encourage collaboration, transparency, and continuous improvement. The result is a streamlined delivery process where changes can move from idea to production more quickly and with fewer risks. From a technical perspective, DevOps is implemented through practices such as continuous integration and continuous deployment, CI/CD, infrastructure as code, automated testing, and comprehensive monitoring and observability. These practices reduce manual work, enforce consistency, and provide rapid feedback loops. The outcome is an environment where software can be released frequently, infrastructure can adapt to demand, and failures can be detected and corrected early. DevOps also aligns with broader business objectives. By enabling rapid and reliable delivery, organizations can respond faster to customer needs, maintain competitive advantage, and ensure secure, stable systems. Importantly, DevOps is not a single framework or tool set. It is a flexible collection of principles and practices that can be adapted to different industries, technology stacks, and organizational sizes. In this book, we will build a structured understanding of DevOps. We will begin with the mindset and cultural principles that support it, then progress to core technical practices such as CI/CD, infrastructure as code, monitoring, and security. Finally, we will explore advanced concepts such as cloud-native DevOps, containerization, and the integration of emerging technologies. The goal is to provide both the conceptual foundation and the technical depth required to apply DevOps effectively in practice. Chapter 2, the DevOps mindset. At its heart, DevOps is more than a collection of tools or processes. It is a mindset, a way of approaching technology and teamwork that focuses on building reliable systems and delivering value with confidence and speed. What makes this mindset powerful is its humility. It recognizes that no single team, role, or tool can achieve success alone. Instead, success comes from collaboration, shared ownership, and continuous improvement. In many organizations, software delivery has been slowed down by silos. Developers focused on features, while operations focused on stability, and security often arrived late in the process. These separations created friction and delays. The DevOps mindset aims to break down these barriers by fostering cross-functional teams where developers, operators, testers, and security professionals collaborate seamlessly, working side by side toward shared goals. In this model, everyone is responsible not only for writing code, but also for ensuring that it runs reliably in production. This shift encourages a culture of accountability and trust. Technically, the DevOps mindset is rooted in a few guiding principles. First is system thinking, seeing the entire software delivery pipeline as a unified flow. It is not enough to optimize only the coding phase or only the infrastructure phase. Instead, we optimize the end-to-end process, from writing code to building and testing to deploying and monitoring. This perspective ensures that improvements benefit the whole system, not just isolated parts. Second is automation as the standard. Manual steps introduce errors and slow down progress. By automating builds, tests, deployments, and even infrastructure provisioning, teams gain consistency, speed, and reliability. Practices like continuous integration, continuous delivery, and infrastructure as code all arise from this principle. Automation doesn't replace people, it empowers them, freeing teams from repetitive work so they can focus on innovation. Third is the importance of rapid feedback. Every step in the pipeline produces valuable signals, whether through test results, monitoring data, logs, or user feedback. A DevOps team listens closely to these signals and responds quickly. This feedback loop is what enables resilience. Failures are not hidden or ignored. They are surfaced early, learned from, and used to make the system stronger. Finally, the DevOps mindset embraces continuous learning. Outages, security incidents, or performance issues are not treated as personal failures, but as opportunities to improve. Blameless postmortems, chaos engineering, and automated recovery strategies all encourage teams to grow and build confidence in their systems. This humble approach, acknowledging that systems will fail, but preparing to recover gracefully, is one of DevOps' greatest strengths. In essence, the DevOps mindset is about breaking down silos, trusting in automation, listening to feedback, and learning continuously. It empowers teams to deliver technology that is both fast and reliable, while cultivating a culture that values humility, responsibility, and growth. This mindset is what unlocks the full potential of the technical practices we'll explore next, because without it, the tools are just tools. With it, DevOps becomes a discipline that transforms how we build and operate software. Chapter 3, CI/CD pipelines. If the DevOps mindset defines why we work the way we do, then CI/CD pipelines show how we bring that mindset to life. At its core, CI/CD is about making software delivery fast, safe, and predictable, so teams can focus on building value rather than firefighting production issues. Continuous integration, merging frequently, failing fast. Continuous integration, CI, is the practice of frequently merging code changes into a shared repository. Each merge triggers automated builds and tests, ensuring that errors are caught early. The principle here is simple. Don't wait until the end of a project to discover that something is broken. CI is more than just running tests automatically. It is a commitment to collaboration and transparency. Developers work in small increments, integrating changes often so that the whole team can see progress and detect conflicts early. By catching problems sooner rather than later, CI reduces friction and builds trust across teams. Automated testing, your safety net. Testing is the backbone of CI. Automated unit tests, integration tests, and sometimes even user interface tests ensure that new code does not break existing functionality. Automation frees teams from repetitive manual checks and allows them to move faster without sacrificing quality. In DevOps, testing is not a gate, it is part of the flow. It surfaces problems early, giving teams the confidence to innovate without fear. Continuous delivery and deployment from ready to live. Continuous delivery, CD, extends CI by making sure every change is deployable at any time. Teams can release updates with a click, knowing that automated tests have verified correctness. Continuous deployment goes a step further. Every successful change is automatically pushed to production. In this model, software delivery becomes seamless and predictable, eliminating long release cycles and late-night surprises. Pipelines turn code into value faster, reliably, and with fewer human errors. Tools that make pipelines work. While the principles are universal, tools bring them to life. Jenkins, the veteran of CI/CD, remains widely used for its flexibility and plugin ecosystem. GitHub Actions provides modern, integrated workflows directly in your repositories. GitLab CI/CD offers an end-to-end pipeline solution for teams seeking tight integration. Other options like Circle CI, Travis CI, and Azure DevOps provide similar capabilities tailored to different workflows. These tools do not replace the mindset, they amplify it. When combined with the DevOps principles of automation, collaboration, and feedback, pipelines become the engine that drives fast, safe software delivery. The benefits: speed, safety, and confidence. CI/C. D pipelines transform software delivery. They increase speed, letting teams release updates multiple times a day. They improve safety, catching errors automatically before they reach production. And they provide confidence, letting developers and operators trust that what is in the main branch is ready for release. Pipelines are more than technical configurations. They are a reflection of a team's culture, mindset, and commitment to excellence. Flow to next chapter. CI/CD. Pipelines are powerful, but they rely on infrastructure. Servers, cloud environments, containers that must also be consistent, versioned, and reliable. Managing this infrastructure manually introduces drift, errors, and delays. To address this, we turn to infrastructure as code, IAC, the topic of the next chapter, where we learn how to treat infrastructure with the same care, automation, and repeatability as application code. Chapter 4, Infrastructure as Code, IAC. CI/CD pipelines. Let us deliver software quickly, safely, and confidently. But pipelines run on infrastructure. Servers, networks, databases, and cloud resources are the foundation on which applications live. Managing them manually through clicks and console commands is slow, error-prone, and difficult to reproduce. Small differences between environments, drift, can lead to unpredictable failures in production. Infrastructure as code, IAC, solves this by treating infrastructure like software, versioned, repeatable, and automated. Declarative versus imperative approaches. IAC can be approached in two main ways. Declarative, you describe what the system should look like, and the IAC tool figures out how to achieve it. Terraform and CloudFormation follow this model. You define the desired state, and the tool makes it real. This approach reduces complexity and ensures consistency. Imperative, you define exactly how to create resources step by step. Tools like Ansible can follow this approach, executing tasks in the specified order. Imperative code gives granular control, but can be harder to maintain at scale. Understanding these approaches helps teams choose the right tool for their needs and workflows. Popular IAC tools. Terraform, a cloud-agnostic tool that allows teams to define, version, and provision infrastructure across multiple providers. CloudFormation, AWS's native declarative tool for defining infrastructure as code, tightly integrated with its services. Ansible, configuration management and automation tool, often used for both provisioning and post-deployment configuration. Pulumi, a modern alternative that allows writing IAC in general-purpose programming languages like Python, TypeScript, or Go. Each tool reflects a mindset. Infrastructure should be version-controlled, automated, and reproducible, just like the applications it supports. Benefits of IAC. Consistency. Infrastructure can be recreated reliably across development, staging, and production environments. Drift and configuration errors are minimized. Versioning. Changes to infrastructure are tracked in code repositories. Teams can review, audit, and roll back modifications just like they do with application code. Reduced manual effort. Automated provisioning saves hours of repetitive work and reduces human errors. Collaboration. Teams can work together on infrastructure changes using pull requests, code reviews, and automated tests. bringing the same culture of collaboration to operations as we have in development. The bigger picture. IAC embodies the DevOps mindset in action. It brings automation, transparency, and collaboration to infrastructure, ensuring that environments are predictable and reliable. Combined with CI/CD pipelines, IAC allows teams to treat both code and infrastructure as a unified, manageable system. Flow to next chapter. With pipelines running on predictable, versioned infrastructure, the next challenge is keeping the system healthy and visible. How do we detect issues before they become outages? How do we understand performance and failures in complex distributed systems? These questions lead us to monitoring and observability, the focus of the next chapter. Chapter 5, Monitoring and Observability. Infrastructure and pipelines are in place, software flows smoothly from development to production, and teams have automated much of the delivery process. Yet even the best engineered systems can fail. Servers crash, network latency spikes, databases slow down, and unexpected bugs surface. To maintain confidence in the system, teams need visibility into how it behaves in real time. This is where monitoring and observability come in. Monitoring versus observability. Monitoring is about tracking known metrics and alerting when something goes wrong. It answers questions like, is the CPU usage too high? Is the database response time exceeding thresholds? Traditional monitoring tools provide dashboards, charts, and alerts, but they often focus on known problems. Observability, on the other hand, is about understanding unknown problems. It uses metrics, logs, and traces to give teams the ability to ask questions about system behavior they may not have anticipated. Observability answers, why did this request fail? Where is the bottleneck? What patterns caused this outage? In essence, monitoring tells you when something is wrong. Observability helps you understand why it is wrong. Key components of observability. Metrics, quantitative measurements like CPU usage, request latency, or error rates. They provide a high-level overview of system health. Logs, detailed, time-stamped records of events and actions in the system. Logs help trace what happened step by step. Distributed tracing, tracks requests as they flow through multiple services, revealing where delays or errors occur in complex systems. Together, these tools give teams a full picture of system behavior, allowing proactive troubleshooting rather than reactive firefighting. Site reliability engineering, SRE, practices. Observability is closely tied to SRE principles, which aim to balance innovation with reliability. Key concepts include SLIS, service level indicators, metrics that indicate the performance of a service, SLOS, service level objectives, targets for those metrics, defining acceptable levels of performance, SLAS, service level agreements, formal agreements with users or customers about expected service reliability. By defining these targets and continuously monitoring against them, teams can make informed decisions about reliability and prioritize work effectively. Benefits of observability. Early detection. Problems are caught before they become outages. Root cause analysis. Faster identification of underlying issues reduces mean time to recovery. MTTR. Continuous improvement. Insights from observability data inform optimizations, architectural changes, and proactive fixes. Flow to next chapter. Visibility into your systems is essential, but modern software also faces security threats, from misconfigurations to vulnerabilities in dependencies. To address these risks while maintaining speed, teams embrace DevSecOps, integrating security into the DevOps pipeline. That's the focus of the next chapter. Chapter 6, Security and DevOps, DevSecOps. Speed and automation have transformed the way teams build and deliver software. But with speed comes risk. Every new dependency, every infrastructure change, and every deployment introduces potential vulnerabilities. In the past, security was often treated as a final checkpoint, a phase at the end of development, where auditors or specialists would comb through code and configurations. This approach slowed delivery and created friction between teams. DevSecOps challenges this model by bringing security into the pipeline itself. Instead of waiting until the end, security becomes part of every step in the process. Shifting left. Shifting left. Security early and everywhere. To shift left means to move security earlier in the development lifecycle. This involves building checks, scans, and policies directly into CI/CD pipelines. Developers get immediate feedback about vulnerabilities, misconfigurations, or unsafe dependencies. Security is no longer an afterthought. It becomes a shared responsibility across development, operations, and security teams. This shift also changes culture. Instead of security acting as a gatekeeper, it becomes an enabler, helping teams move fast but safely. Security automation in pipelines. Modern DevOps pipelines weave in automated security checks such as static application security testing, SAST, analyzes source code to detect vulnerabilities before code is even run. Dynamic application security testing, DST, tests running applications for exploitable issues. Dependency scanning identifies vulnerabilities in third-party libraries, a common source of risk. Container scanning ensures images are free from known vulnerabilities and misconfigurations. Automating these checks means developers receive feedback early and risky code is caught before it reaches production. Compliance as code. In many industries, security is not just best practice, it is a regulatory requirement. DevSecOps brings compliance into pipelines through compliance as code, where policies and standards are codified and enforced automatically. Instead of waiting for lengthy audits, teams get continuous assurance that systems remain compliant as they evolve. This proactive approach reduces the stress of last-minute compliance checks and creates confidence in meeting regulatory standards. The benefits of DevSecOps. Speed with safety. Teams deliver quickly without sacrificing security. Reduced risk. Vulnerabilities are caught before reaching production. Shared responsibility. Security becomes everyone's job, not just the security teams. Trust. Organizations build confidence with users, stakeholders, and regulators. Flow to next chapter. Security ensures that fast delivery does not come at the cost of safety. But modern applications are no longer confined to traditional servers. They are built with cloud-native technologies like containers, Kubernetes, and serverless platforms. To truly understand modern DevOps, we must explore how the cloud-native era reshapes practices and possibilities. That's the focus of our next chapter, Chapter 7, Cloud-Native DevOps. Software delivery has always been shaped by the environments it runs on. In the past, applications were hosted on physical servers, then on virtual machines. Today, we've entered the era of cloud-native computing, where applications are designed from the ground up to take advantage of the flexibility, scalability, and automation that the cloud provides. For DevOps, cloud-native technologies are not just tools. They represent a new way of thinking about how we build, deploy, and operate systems. Containers and Docker. Containers change the way we package and run applications. Unlike virtual machines, which carry the overhead of an entire operating system, containers are lightweight and portable. Docker made this concept accessible, giving developers a consistent environment from laptop to production. With containers, "It works on my machine" is no longer an excuse. The same container image runs reliably everywhere, eliminating one of the biggest sources of friction between development and operations. Kubernetes orchestration. But as teams adopted containers, another challenge emerged. How do you manage hundreds or thousands of them at scale? This is where Kubernetes came in. Kubernetes automates deployment, scaling, and management of containerized applications. It ensures that workloads stay running even when individual machines fail. It provides self-healing, service discovery, and resource management, all the building blocks needed to run resilient applications in the cloud. For DevOps, Kubernetes represents the next level of automation and reliability. It enables teams to focus on delivering value, while the platform handles the complexity of scaling and resilience. Serverless and microservices. Cloud-native DevOps also embraces serverless computing. Instead of managing servers at all, teams deploy small functions that run only when needed. AWS Lambda, Azure Functions, and Google Cloud Functions allow developers to focus purely on code, while the cloud provider handles scaling and infrastructure behind the scenes. Alongside serverless comes microservices architecture, breaking large monolithic applications into smaller independent services. Each microservice can be developed, deployed, and scaled independently, enabling faster iteration and greater resilience. This approach aligns perfectly with DevOps principles of speed, automation, and shared ownership. GitOps and automation in the cloud era. The cloud-native movement also gave rise to GitOps, where Git becomes the single source of truth for both code and infrastructure. Changes are proposed through pull requests, reviewed by teams, and automatically applied to the environment. This unifies collaboration, automation, and observability, making cloud operations feel like software development. GitOps brings clarity and confidence to complex cloud systems, reinforcing the DevOps mindset of automation, transparency, and continuous improvement. The benefits of cloud-native DevOps. Scalability. Systems automatically adjust to handle demand. Resilience. Self-healing platforms recover from failures without manual intervention. Speed. Teams can deliver features faster with less overhead. Innovation. Freed from managing infrastructure, teams focus on creating value. Flow to next chapter. Cloud-native technologies show us what's possible when DevOps meets the full power of the cloud. But practices and tools mean little without real-world application. To see DevOps in action, we turn to case studies and stories, lessons learned from successes, failures, and everything in between. That's the focus of our next chapter. Chapter 8, The Future of DevOps. DevOps has already transformed how organizations build and deliver software, but the journey is far from over. As systems grow more complex and expectations rise, DevOps itself is evolving, absorbing new practices, new technologies, and even new identities. The future of DevOps is not just about faster pipelines. It's about building intelligent, resilient, and developer-friendly platforms. AIOps, Intelligence in Operations. One of the most exciting frontiers is AIOps, the application of artificial intelligence and machine learning to IT operations. Imagine monitoring systems that don't just alert you when something is wrong, but also predict failures before they happen. Logs, metrics, and traces generate massive amounts of data, far more than humans can analyze in real time. AI can sift through these signals, identify patterns, and surface insights that humans would miss. In the near future, outages may be detected and even resolved automatically, reducing downtime and freeing engineers to focus on innovation. Platform engineering, a DevOps evolution. As organizations scale, developers often face cognitive overload. navigating cloud services, deployment scripts, security policies, and observability tools. Platform engineering addresses this by creating internal developer platforms, IDPS, self-service systems that abstract away complexity and give teams golden paths for building and deploying software. In many ways, platform engineering is DevOps maturing, turning years of hard-won practices into standardized, developer-friendly experiences. Instead of every team reinventing the wheel, platforms provide consistency, speed, and safety at scale. GitOps maturity. The practice of GitOps, using Git as the single source of truth for both code and infrastructure, is becoming more widespread, but its maturity lies in automation and policy enforcement. In the future, GitOps will not only handle deployments, but also enforce compliance, security policies, and architectural best practices automatically. Every change, no matter how small, will flow through a transparent, reviewable process that strengthens collaboration and trust. Autonomous pipelines. If the earliest DevOps pipelines automated builds and tests, the future pipelines will be self-optimizing systems. They will adjust automatically based on context, rerunning tests only where risk is high, scaling infrastructure to meet demand, or rolling back safely without human intervention. These autonomous pipelines will blur the line between development and operations, creating a seamless flow from idea to production with minimal friction. A mindset that endures. Even as tools evolve and new practices emerge, the heart of DevOps will remain the same: culture, collaboration, and continuous improvement. The future will bring more automation, intelligence, and abstraction, but success will still depend on people, how they share responsibility, learn from failures, and adapt together. Flow to next chapter. We've looked at where DevOps is heading, from AI-powered operations to autonomous pipelines. To close this journey, we'll step back and reflect on what ties it all together: the culture, principles, and practices that make DevOps more than a job title. That's the focus of our final chapter, Chapter 9, Beyond DevOps. DevOps has carried us a long way. It broke down silos, introduced automation, and gave teams the ability to deliver software with speed and confidence. But the landscape is still shifting. Complexity is growing, expectations are rising, and new technologies are pushing us to ask, what comes after DevOps? The phrase "beyond DevOps" doesn't mean leaving it behind. Instead, it means building on its foundation, taking its principles of culture, collaboration, and continuous improvement into new territories. AIOPS, smarter operations. As systems generate vast amounts of data, humans alone can't keep up. AIOPS uses artificial intelligence to analyze logs, metrics, and traces, detecting anomalies and even predicting failures before they happen. Instead of drowning in alerts, teams gain actionable insights. Beyond DevOps, operations won't just be automated, they'll be intelligent. Platform engineering, from practice to product. In many organizations, DevOps has evolved into platform engineering. Instead of every team building its own delivery pipeline, internal developer platforms, IDPS, provide golden paths for development, deployment, and security. These platforms reduce complexity for developers while ensuring consistency and compliance at scale. Beyond DevOps, the focus shifts from individual practices to curated platforms that empower whole organizations. GitOps and policy-driven automation. GitOps has already redefined how we manage infrastructure and applications. But in the next stage, GitOps will integrate with policy-driven automation. Compliance, security, and governance won't be afterthoughts. They'll be codified in the same workflows that deliver applications. Beyond DevOps, Git becomes the universal language not only of code, but of operations and policy. Autonomous pipelines, from automation to autonomy. If pipelines today automate builds and deployments, tomorrow they will become autonomous systems. They will optimize themselves, run only the tests that matter, scale resources dynamically, and roll back safely when issues appear. Teams will focus less on maintaining pipelines and more on guiding strategy as the system itself adapts in real time. Culture that endures. Despite all the innovation, one truth remains. Tools will change, but culture endures. Beyond DevOps, success will still depend on humility, trust, and continuous learning. Outages will happen, systems will fail, but the ability to recover quickly, share responsibility, and learn from failure will remain the beating heart of modern technology teams. Flow to next chapter. Beyond DevOps, we glimpse a future where systems are smarter, platforms are more unified, and pipelines are increasingly autonomous. But the principles stay the same: collaboration, automation, measurement, and sharing.